Hi everyone. I logged out and logged in somehow. I was logged in with another account and I couldn't record, but let me check that everything is okay now. So I had to do some demo to write a demo how to use Zoom, and I created like 3 accounts, and somehow I was logged in with another account and I couldn't record this session. So let's see. Okay, today is 24. Yeah, it's fine. Yeah. Okay, it's written recording here. Okay. Now it's recording. Okay, let me share the screen. Where is my screen? Where is my screen? Okay, my screen is here. Okay. Share screen. Share screen. Okay. Okay. Now it's fine. Let's go. Okay. We'll do it like this. Okay. I need the chat stuff. Okay. Okay. Let's start. Okay. So before we start the class, there is some stuff that I want to say. So I talked to Juliana, and she said that it would be a good idea to put on the web some data, such some additional data, and I see this additional data like a validation set for project 1. And the idea is that we put some data in order for you to get use with the format that we're gonna use for evaluating your project. So if you look at the data, there is another folder there, additional data, that consists of 4 folders. And these 4 folders will have some files that will correspond to some format of images that I was talking in lecture 4. So if I go forward, in lecture 4, I told you that in the scenario 1, we will evaluate your project by giving you 55 scanned images, 01, 02 to 55, and the name scanned. And you have also the annotation there. F is for physics, 1 is for variant 1, and so on. And what I put on the web is that, so I put like 5 images in for scenario 1. So I started with number 56, just not to confuse with the first 55. So you have like 56 underscore scanned underscore F2, meaning that this image it's a scan version, and it had physics and number 2 and so on. So you have 5 scanned images here. You have 10 images in the folder called rotated plus perspective, and if you look at them, so in the test set that you're gonna receive after Easter, you'll have from 1 to 100. So I put the number here from 101 to 108, 110. I think there are 5 rotated and 5 perspective test sheets. And what I want to clearly stress out is that these images, they don't appear in the training data. So basically, these images are part of our test minus training data. These images were until now only available to me, but Juliana convinced me that it's a good idea, and I also think that it's a good idea to put this on the web, such that you will write your software such that it will read these kind of images and it will produce the output that we expect, meaning that we want from your software to produce a number, which is basically the grade assigned to a test sheet. So in this folder we have 10 images, 5 rotated and 5 perspective. But here you also have the annotation. You do know the view, what the candidate has chosen, either informatics, either physics, and the number of the variant. Scenario number 3 with no annotation. This is basically one of the hardest one. So if you look here, you see that 76, 77, and 83 are scan views of the test sheet, and the other ones are perspective and rotation. And in the last folder, handwritten, I only put 3 images, 26, 27, and 28, because so you will receive from us 25 images. So these are images on which you should detect basically the grade, the handwritten with the red color. And what I did to all these 3 images, so I think I played with some pixel in Paint or in GIMP. I didn't know what I used, such that I modified the images such that if you employ a perfect automatic solver for detecting the X marks and finding a way to compute the grade, this will not be the same as the one that is handwritten there. So here you have like 790, and here you have a 790. And if you look closely, you see that in the left image, what I did, I copied an X here. So I put on the 6th row here, there are 2 X's, such that this answer becomes invalid. And I think I did something else. Yeah, so at one point, I put 2 X's here in the right frame on the 14th row, and I moved, so I deleted an X from the last row here, such that, so I did some actions. If you try to come up with the grade, no, so actually the handwritten grade, it's not wrong. So you want to detect the handwritten. You are not interested now in detecting coming up with the grade by analyzing the left and the right frames. So you don't have to take into account these ones. You only have to come up with a solution to say that in the red color it's even 790. So my actions were made in order to not to trick you, not to use your software to say that here it's 790, because if I didn't do anything, so if I wouldn't have done anything, then just by using your software, you could have said that here it's 790. So this is a bonus point, and it's a hard part of your project, but you should manage to do something. I don't expect that you should solve all the 25 images correctly, but it should work on some percent, and basically this will be a bonus for you. Okay. Okay. Any questions regarding this stuff? So I'm pretty sure that you will be glad that you will have these additional images. I remember that some of the students asked me during the lab session, also in the faculty and also online, that if the distribution of the test data is the same with the distribution of the train data, and here you have around like that there are like 15 or 20 different images that shows you that what you'll get is basically the same stuff that you have for training. So do we have to output all the results in a specific manner? Yeah, so you have to write the grade number of correctly question answered by a candidate. So you should so if I go back here, if you are in this scenario and you would maybe I go to this stuff. Okay, maybe I go to this one. So yeah, it's not clear. So if you receive image number 76, you have to output the grade. So just one number. Okay. Okay, let's try another question. Yeah, so in the fourth scenario, the idea is that you will recognize the handwritten. Yeah, so you want to recognize this 7.90. Okay. Not taking into account the answers, yes. Of course, that you can do some tricks and see basically that this grade it will belong to a class, yeah. So actually, you cannot have like 780. Yeah. So input of the script is the file name, yeah, and the output should be the grade, yeah. Exactly. So either you see the grade is a float number 790, or you see it as the number of correctly answered question, like 23 times 0.3, it's 6.90 plus 1, it's 7.90. All the two answers will be correct. The grade is always in red. The number of the test sheet it's always in green. So everything it's the same. Yeah. So you only have to take the red part. Okay. Other questions? You can also ask me with sound. Okay. Yeah.
Can you use like OCR libraries for the handwritten recognition part?
You can. Yeah, you are free to try this stuff, but I'm pretty sure that they will not work.
Okay, thank you.
So you are allowed to do this stuff. It's fine.
Okay, thanks.
I mean, we try with at least with my writing, and it doesn't work at all. Okay.
Okay.
So then what's a good approach to recognize it if the OCRs don't do so?
Yeah, so actually this is a bonus point, so I'm not supposed to give you some hints, but you can take some convolutional neural network and see back in the 90s what LeCun did to recognize handwritten for checks. So if you Google LeCun convolutional neural network recognizing digits for checks, it might work. And if you so what does the red text under the grade? So it's my signature. B Alexei comes from Bogdan Alexei. So there you have the grade is 7.90, and it is also written 90%. Yeah, so it's only one signature. Yeah. Yeah, only one. So actually, so the rule is that one vice dean has to put the grade with red.
Can we also try using pre-trained models?
Of course.
For OCR, all right.
Of course, yeah. You are free to do whatever you want to solve this problem. So one indication is that you could look what LeCun did back in '98 when he trained a neural network to recognize digits written on checks, and this software was delivered to U.S. Postal to process all these checks. And of course, I mean, you have like 150 training examples, and if you really think about it, you have like 30 classes, yeah, and 30. You could say that basically each candidate did I don't know, between 10 and 25, 30 correct answers. So basically, you have only 20 classes. Like, so if he solved correctly 10 questions, you have like 10 plus 10 times 0.3, it's 3 points plus 1 point, it's 4. So you have 4, 40, 460, 490, 520, and maybe this will be a good indication for you. Okay, so you don't have to so you have to pay attention that not all grades are valid. A candidate cannot take here like 7.85. Yeah, it's only 790 or 820 or 850, and this maybe will help you a bit. Okay, any other questions regarding the additional data that we put on the web? Yeah, maybe if you have questions, maybe you can ask me on the email or during the lab session. So don't forget that today from 6 p.m. you have lab session with Juliana. She will do the same stuff as last week. Also tomorrow morning I'll do the same stuff that I did last week. If you are present last week, you could intervene in the beginning and ask me questions, and then maybe you can stay, but basically I will solve the same stuff again. I think also there is some video, yeah? If I remember well, I did the recording, but no problem, I will record again. Okay, maybe we move forward. So let's recap what we did last time. So last time we talked about half transport, which is a technique like also so is a technique that using a voting scheme, and we use it, or actually you can use it in your project to detect straight lines. So here in the image space, you have some edges that are sitting on a line, and the basic idea is that each edge will vote for a line or for a set of lines that will pass through the point in the image. And in the half parameter space, you have to find the parameterization for the line, and in this half space, you have to discretize your parameters. And each feature point in the left image, and when I say feature point here, I'm referring to an edge. It's a pixel on an edge. It will vote. It will vote to a cell here, meaning that here you will have cell accumulating votes. And in the end, after you process the entire image, the cell that will have the highest number of votes will basically represent in parametric form. It will represent the line that casted the largest numbers of votes. So let's remember what we did last time. So we saw that there is a correspondence between the image space and the half space, and you have to remember that a line in the image space, when you have the parameterization based on the slope and the intercept, so if you express a line like y equals m times 6 plus b, where m is the slope and b is the intercept, then to a line it will have parameters slope m and intercept b. So a line in the image will correspond to a point in the half space, and also a point x0, y0 in the image will map to a line in the half space. So here, if you consider x0, y0 equals 1, 1, then all the lines that follow this parameterization, y equals mx plus b, that go to the point 1, 1, should fulfill the relation 1 equals m times 1 plus 1. So if you replace y with 1 and x with 1, you will obtain an equation in M and B, which is basically the equation in the parameter space that will correspond to the point to x0, y0 in the image space. And we saw that if you use these two observations, basically if you have 2 points here, x0, y0, and x1, y1, you could find the lines that go through all these 2 points by finding the intersection of the lines that are defined by each point. So x0, y0 defines this equation, b equals minus x0 plus y0. x1, y1 will define the equation, the line in the half space b equals minus x1 plus y1. When you take the intersection, you will find a point that sits also on this line and also on this line. This basically will be a point b star m star that defines a line that contains that passes through all these 2 points. So it will be exactly this line. So basically these 2 points will vote for this parameter, b star m star. Now there was a problem with the parameterization of a line given by the slope and intercept, because for vertical lines you would have infinite slope. So you could tackle this problem by binning the x-axis for the slope in a logarithm manner, but also this could be problematic. So a better way is to parameterize a line in the image space is to use another parameterization for the lines in the image space. So for each line in the image space that passes through the point x, y, you could parameterize a line by 2 parameters d. D is the distance from the origin to the line that is perpendicular on your line that contains point x, y. And you could also parameterize your line based on theta, the angle that is perpendicular on the line makes it with the OX axis. So if you do all the math, then you will see that to each point x, y, it will correspond. So the set of all possible lines that pass through the point x, y in an image is given by a sinusoid curve in the half space, and the equation of this sinusoid curve, it's d equals x cos theta plus y sin theta. If you had the other parameterization, this curve would have been a line. So here you would have obtained minus b equals x times m plus y. I think this was the relationship, okay, or something like that. Okay, and we remember that sinusoid curve. So here you have a drawing for this sinusoid curve. This is actually a sinusoid curve that corresponds to the point x equals 1 and y equals 1. So what I did here, I took all the lines that have theta go from 0 to 360, something like that. Yeah. So I took theta and I discretized theta in 100 values. So 360 over 100. So I took each line to have an angle like 3 or 4 degree, 3.6 degrees, and then plot all the lines based on the d and theta pair that characterizes each line in part. Okay, and we finished last time by giving an algorithm for detecting lines, basically finding the parameters d theta from the accumulator array H that will have a local maximum of vote. So there are a couple of versions. The general version of the algorithm is that for each feature point, so basically for each edge will vote for all possible direction basically for all the lines that could pass through the point XY. So you'll go from theta with some discretization pass from 0 to 180, and so here each point votes for basically for all direction of lines, and the vote of each edge has the same importance 1. And the idea is that you accumulate all the votes in the matrix H, and then when you then after each of the edges has voted, you go to your H, find the local maximum values. You find the theta star and D star, which correspond to the cell with the maximum number of votes, and then your detected line in the image will be given by the equation where D and theta, D star and theta star are known because you have determined based on your matrix H, and X and Y will be your unknowns. So you will see this equation in X and Y, and we have modified this version such that, so one possible modification that it will also make the algorithm very fast is that instead of allowing each edge to vote for all possible lines that pass through the current point, you will say that you have computed for the current point XY your theta, and basically theta, you know that an edge is perpendicular to your line. So basically this theta will define the direction of your line. So in this case, you will allow a point just to vote for just one direction theta. So instead of having 2 4s, now you have just 1 4. And another change to your algorithm is that instead of saying that each edge has the same importance in voting, you would say that each edge will have an importance given by the magnitude of the gradient. So if you employ the gradient orientation, you will allow to an edge to vote only for just one line. And if you employ the gradient magnitude as the importance of your vote, you will say basically that if a pixel has a higher gradient, then the vote will count more. Okay, so this was what we did last time. What we will do today is to finish the half transform part, and also to tackle the stuff that we didn't tackle last time. And today we're going to talk about color. Color, it will be an important feature, especially for your bonus point, because based on the color, you can recognize you can at least recognize the part. You can detect the part in the test sheet where the grade is, and then you should use some machine learning approaches in order to recognize your handwritten grade. Okay, so last time we talked about half transform to use it for straight lines, and you could use it for your project. It should work. I play with it, and it works really well. Now, in this lecture, I'll talk about how to use it for detecting other shapes like circles or general templates. And we will also see that you can use half transform to do object recognition. I'm gonna talk about a paper that was written in 2006 or 8, something like that, and it is quite a good paper, and it is working for me and for you to know how you can employ half transform to detect objects. Okay, so now if we want to detect circles in an image, of course, so we move to lines which had 2 parameters. either slope and intercept, or the angle theta and the distance d, to another parameterization. Circles have like three parameters. They have a center x, y, and a radius r. So we will have one dimension more. Then another question that we have to answer is that, given an unoriented edge point, what are all possible beings that it can vote for? We know that for the straight line case, an edge could vote for all possible lines. Now it should vote for all possible circles. We do know that if we have chosen for the straight line the parameterization d theta, an unoriented edge would have voted for a sinusoid in the parameter space. Now we have to see an unoriented edge point in the image space will vote for some shape in the half space. And if we take the theta, if we know the orientation of our edge, what will happen in this case? Okay, so the equation, the parameterization of a circle, it's this one: xi minus a squared plus yy minus b squared, it's equals r squared. So a point on a circle of center a, b, and radius r has distance r from the center. Now we distinguish here two cases. One case is that we know the radius r of the circle that we are looking in the image. So if you know your r, then in the, let's say that you have some edges, or you have some edges on your circle here, and you want to find x, y, and yy. So basically a and b will correspond to x, y, and yy, and you like that each point to cast a vote here. Now, because this edge, so this edge is on the circle, the possible set of all center will be on the circle that is at radius r, that is on the radius r, that is its center on this edge point, and it's at radius r on the circle. So this point basically will vote for all possible centers that have radius r and could contain this point. It's represented by a circle. So you'd have that to this point will correspond a circle, to this point will correspond this circle, and to this point will correspond this circle. Now, if you take the intersection of all these three circles, basically you'll find the point at the intersection of that three circles that is basically, this point will be the center of the circle containing in the image space of the three, all of the three edge points on the circles. So you have found here the point that is at the intersection of all the three circles. So basically, each point will vote here for also, like in the straight line cases, it will vote for some cells where x-axis is the location of the xy coordinate, and this will be the second dimension accounts for the yi. So where you have when you have a fixed radius r, everything is fine. Now, if you don't know the r, so basically you could have circles of different radius r that could pass through your edge point in the image. Now, now we have to answer. So what will correspond to a point here? We do know that in the fixed radius case, to a point in the image space will correspond a circle in the half space. Now, because we have unknown radius r, you could see this case. You could split this case in the following. You could fix an radius r, and we do know that from the first case to a radius r will correspond a circle. Now with a circle with the center in this point, now because you have an unknown radius r, this will mean that you have different circles, different circles, and because now you have 3 dimensions, so now you also have to vote. So you vote for the center x, y, 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 and you also vote for r. So in this case, you will vote for each r, you will vote for a circle, and this basically it will mean that a point here will vote for a cone. Yeah. So you have R, I, A, B. If you fix r, you will have a circle, and then if you make r to the radius r to vary, you'll obtain a cone. Yeah, so you'll obtain this kind of stuff. Now, if you have 2 votes, if you have 2 edge points, of course that you'll obtain 2 cones. Now, of course, that here there is an infinite number of circles in the image space that will pass through all these two points. Just take the segment here and take the perpendicular on the segment of these two points, and on this perpendicular, each point can be the center of a circle that passes through all these 2 points. Of course, that you need another point such that you will find the solution. So just remember that in this case, when you have an unknown radius r, you will have that each point, basically to each point in the image space will correspond a cone. Now, if you have if you know the gradient direction of your edge, so instead of voting for all possible direction, now you will allow your edger to vote just for one direction. So instead of having circles here, you'll just have one point out. So this basically means that your cone will be just a ray. So in this case, you'll have just a ray. Now, if you have these two points, you'll have 2 rays, and that ray should meet. Now, let's go to an example. So in the left image, you have some coins, and the idea is that you want to detect coins which have a circular shape, and you are in the scenario where you do know what is the length of each ray. So in the first case, so you extract edges, maybe with Kenny, and then if you do know what is the length of the shortest ray, then you will employ half transform. Each of the points, each of the edges will vote, and the higher number of votes will basically mean that the center of a circle with this radius of known size, it's here. Now, if you employ the half transform for the second ray, so you have coins with 2 different rays. Now you will obtain 3 different centers here, here, and here. Okay, and basically in the end, if you combine the detection from the 2 votes, so you will obtain the centers of your detection here, and so you'll obtain your detection here, and you see that the noise from edges it's gone. Okay, let's see some arguments, pros and cons for this method. So one thing that we also will encounter later, we will see that half transform can deal with occlusions, because there will be still some votes that will vote for the right parameters of your model. You can also detect multiple instances of a model, and of course that you have some robustness to noise, because edges that are noisy and they should not be in the image will vote for some models, for some hypotheses that will be inconsistent. And the basic idea is that this inconsistent hypothesis will cast just a very few number of votes. Now, as drawbacks for the Hauff transform, of course, that if the number of model parameter increases, so until now you saw straight lines with 2 parameters, circles with 3 parameters, but you can have also more complex models. Then of course you will have now a vote. So in the circle case, you saw that now you have a 3D space. You have to find the cell which have the optimal R, the optimal A, and the optimal B. Of course, that if you go to many dimension, you have the cost of dimensionality. So of course that it will be hard there also to search, but also to find a good solution. Of course that non-target shapes can produce some peaks in parameter space. If you have an image and you have a textured region, in your textured region you can basically fit every hypothesis. You can fit a triangle, a line, or a circle, because you have many noisy edge points in textured area that will cast votes, and this will basically conduct to false positives for your Hauff transform. And of course, it's hard to pick a good grid size. Grid size here means that you have to choose the length of your beans, how large, or how large is the cell area in your space. Okay, now if we move from straight lines and circles to general shapes, we found what is called general Hauff transform. So here the problem is that we want to find a template that is defined by its center, its reference point, and we have several distinct types of landmark points in a stable spatial configuration. For example, you can think of that maybe you want to find a square, and as feature as distinct types of landmarks in a square, you have four corners, and each corner basically will vote for the center of your square. Yeah. So how you would represent here? So you'd represent your model by memorizing the displacement vector of each of your landmark points if each of your landmark points with respect to the center of your shape. So for a square, you have 4 corners, and for each corner, you know what is the displacement vector to the center, and you put this in a database. So for this template, you have these types of landmarks. So for a triangle, you would have like 3 possible displacements with respect to the center. For this is a diamond, also like a rotated square, you will have also like 3 possible displacement. And for the red point, a red ball, you have just 1 possible displacement. Now, if you go to a test image, so at the training time, you build your databases of displacement vector from a landmark point to the center of your object, and to the test at test time, you have the image. You detect the landmark points. For example, if you want to detect squares, you detect corners, and then you go through your database and see that each corner will point to the center of your object. So here you have detected this diamond. You go through your database and apply this 3 displacement vector. this. So basically, this diamond landmark point will vote for 3 possible location of the center. Somehow I didn't put here the third vote. Then you go to the triangle. The triangle in your database will vote for 3 possible location, and so on. So from each landmark, you'll accumulate votes from diamond, from the red point, from the red point, from the diamond, from the triangle, and from the diamond. And in the end, you'll find out that a cell representing the center of your template will accumulate a large number of votes, and this will localize your shape. Okay. Now the idea here that until now I presented basically half transform applied to some synthetic images, but half transform is not just some useless method, but it's actually a method that it's used in object recognition. And basically here, if you have a paper from 2004 where the idea of using half transform in object recognition was used in the following sense. So at training time in an image, the method extracts what is called visual code words. These are small patches in an image which have some photometric properties. So you extract these visual code words at some interest points, some points with some geometric property in the image. Then you build up a patch around these interest points. So these patches are here in cyan. You describe the visual content of these patches with a descriptor, and this descriptor basically it is what is called visual code word, and you retain for each visual code word what is the displacement vector with respect to the center of the object that you are interested to detect. In this case, you have, for example, some code words, some visual code words that, so usually a visual code word, it can be related to a part of your object. And here you see that there are visual code words represented for the wheels of your machine, and for each visual code word you index their displacement to respect with the center. And at the test time, what you do is that you detect interest points, you extract patches, you try to see what is the closest visual words from the vocabulary that you learn at training time. So for example, you have detected wheels here, then you go into your database and apply all the displacement vector for each code word, and see that basically each code word will vote for some centers of your object in the image, and the center of course will cast some votes. And of course that in this image you see that the center localizes very well the cars. So the steps of the method that is described in this algorithm are the following. So at the training time, you build a codebook of patches around the extracted interest point using clustering, and here you see that similar patches that will correspond to the same visual code book are here. You see different parts of a wheel, and also some parts of the shield of the car. Now, so then you map the patch around each interest point to the closed book entry. So you have this assignment from, for example, from the k-means clustering, and of course that you're gonna store all the position, the displacement with respect to the object center. And at the test time, what you do is that you extract interest point, you extract descriptor for each patch, then you assign to each patch the corresponding code book in the visual vocabulary that you learn in the training phase. Each code book, each code word will vote for a center, and then you accumulate in the voting space votes, and then, for example, here you localize the maximum in the parameter space of the vote that will correspond to the center of your object, and then you can refine your hypothesis such that in the end you're gonna localize your image here, a car, and you also can provide a segmentation based on the segmentation that you have at training time, because you do know how to segment part of the object at training time. So here you see additional examples, and so here you see that it works quite well for motorbikes, large big motorbikes, and also small motorbikes. Here also this one is occluded and it's still working fine. It's working also for pedestrians. It's working quite good also for cars that are occluded, and also for cars. This basically was a state-of-the-art method in 2008 employed for detection and segmentation. These are high-level computer vision tasks that we're gonna encounter in the second part of the semester. Of course, that in these days there are other cool methods that, of course, employ deep learning stuff and work much better and much faster. So you will employ these methods for example, for segmentation, you could employ a convolutional neural network, and it is a very known method by Girshik and the other guys. Girshik in ICV 2017. The mask RCNN, which worked very well. But as I said in the beginning, we're not gonna cover we're not gonna cover computer vision methods that rely on deep learning. We will only cover computer vision methods that rely on classical approaches until 2012. Okay. Okay. Now we move to the second part of the lecture, color, and this will be very useful for you to, as I told you, to solve the problem of handwritten recognition of the grade. Here you also have a video. Just one moment. So you have here a video showing how you can use color to discriminate. Something is wrong here. Okay. So it should work. I think we also have a sound. So here you see a machine that sorts tomatoes, discriminating between those that are red and those that are green. It's a very simple method, because the only thing that it has to do is to recognize color red. So it has to separate green from red, and all tomatoes will be separated from the bad ones. Okay, I think you got the idea. Okay, so I will talk about color from two perspectives. One perspective will be from the biological perspective, and I'll talk about how the human visual system process colors, and the other perspective will be from the physics perspective, where basically you have that color is a property that is encountered when the visual system encounters lights, and we will talk about this stuff. So how does the human visual system works? So actually the visual system, the human visual system is very complex. We do know that humans use their eyes as a camera, and the light passes through the cornea and hits the retina, and there on the retina there is a very small region which is called fovea, which basically everything happens there. Fovea is responsible for the central vision. On the retina, you have these photosensitive cells that will gonna absorb the light and transform it into an electrical impulse that it will be delivered to the visual cortex through the optical nerve. Now here you have a simple diagram of the organization of the retina, and here you have the photosensitive cells, which I'll call rods. Rods in Romanian, rods means bastonașe, I think, and cones means conuri. The photosensitive cells, rods, are responsible for the nighttime vision, and basically these are very sensitive to black and white inputs, whereas cones that are very sensitive to color. And from here you can see that there are three types of cones. You have red cones that are sensitive to red color, and you have green. You have green cones, and you have blue cones. And basically through these cones we're gonna perceive color, and this is basically the answer why we have RGB images. Now a little some words about each photoreceptive cell. So cones, in Romanian we call it conuri. There are around 6 million. They have a fast response time, and mostly are packed into one region where central vision happens, and this is fovea. And cones are the main responsible for our color vision during daytime, whereas rods, there are many more. There are 20 times more rods. These are called bastonașe. So they could operate in low light condition during night vision. So they are responsible for night vision, and they have a very slow response time. Now here you have a picture. So on the retina you have a very small region called fovea. So it's a small circle on the retina, which is densely packed with cones. Here you can see that at around fovea there is a very small region which has a very large number of cones, around 200,000, and is the region with the highest visual acuity from the retina. It's responsible for sharp central vision, and basically fovea explains why we move our eyes, such as we move our eyes when we read something. So we do this movement such that the text is the center in fovea. Now, what is the connection between brain and vision? So the electrical impulses, which are transformed by the photoreceptive cells, cones and rods from the light, that are transmitted to the visual cortex through the optical nerve. Now, the visual cortex is responsible for 2/3 of the electrical activity in the brain, and it's like 30% of the cerebral cortex. We do know something about how the visual cortex works, but we don't understand it. We don't understand it fully. So there are a lot of things that we don't understand. For example, we don't understand how the brain processes the inputs that come from the visual cortex. So we don't understand how the visual cortex in the brain processes these kind of images, because these are images that don't make any sense. Usually we try to the brain try to explain what our eye sees, but here you see that there are some images which don't make any sense. And in this particular example, we don't know how the brain interprets the electrical signals that receives from the retina. Okay, now from the physics point, you see that color it's an electromagnetic wave detected by the eye, and of course that it's interpreted by the brain. There is just a small interval of visible light in the electromagnetic spectrum that goes from the range in wavelength from 380 nanometers to 780 nanometers. Now, we can describe each light based on the relative spectral power of each wavelength. We do know that the sunlight contains basically all the wavelengths with different intensities. And here, for example, you have the spectra of some different light sources. You see here, for a ruby laser, you only have basically a wavelength corresponding to the red color. For a gallium phosphide crystal, you have some wavelengths corresponding to the yellow and some green color. For tungsten light bulb, you have a light which is basically containing yellowish and reddish light. You have the spectral relative power. It's much larger for this wavelength than for the wavelength in the left. And for a normal daylight, you have some uniform spectral power for all the wavelengths. Now, here you have some reflectance spectra of some surfaces. You see for how the spectra looks for the red tomatoes. For the yellow bananas, you also see here that you have some red stuff, yellow and also green. We'll counter later green to see that basically people are more sensitive to green. Here you see for this image, you see that you have a peak for the blue wavelengths, and for the purple you have a peak in the left and a peak in the right for the violet and for the red wavelength. Now, if we measure the human eye sensitivity to every wavelength, we'd obtain what is called the standard human luminance sensitivity function. Is this function in white, which has the graph here, and which basically says that the human eye is very sensible to red. So if you to green. So the human eye, it's very sensible to green, and this can be proved easily if you look at this slide where you have a text written in blue and a text written in green. You see that it's much easier to read the text in green compared to reading the text in blue. And so actually, so we are sensible to green basically because in the sunlight you have a lot of green there. I'm not sure that is kind of bigger. Okay, yeah, maybe you are right, yeah. Okay, so so we do know that light is a spectrum. Now, why are images RGB? So images are RGB because our photo receptive cells, our cells are very sensitive to red, green, and blue. And I think you remember these slides from the first or second lecture when we talk about the Bayer filter that it's used to transfer the incoming light in in values for the red, green, and blue channel. And here you see a motivation, a reason why you have so many grids with green green filter than red and blue, and this is because humans are more sensitive to green than to red or blue. Okay, so now we have RGB images because the photosensible cells, the sensitive cells are they are sensitive to some wavelengths. There are three types of wavelengths, which basically they have the peaks around blue, green, and red. So so for cones, the sensitive cells that are responsible for the color vision. You have like three types of cones. You have short cones that they have a peak around 420 nanometers, which corresponds to the color blue. You have medium cones which have a peak around green, 530, and then you have long cones which have a peak around 560, which is around red, while rods which are responsive for the night vision, black and white images, black and white stimuli, they have a peak around 498 nanometers. Okay. Now the number of cones in the fovea here, it's not exactly the same. So we have much more cones that are sensitive to that are sensitive to red. So actually the ratio of long to medium to short cones, it's about 10⁵ to 1. And actually there are no S cones basically which are sensitive to the blue color in the center of the fovea. Now, our photosensitive cells, rods and cones, they are responsible for perceiving the colors. What they do is actually they act like filters on the spectrum. So given a spectrum of a wavelength, they act like a filter. So for example, the long cone will filter basically the wavelength, also the medium one and the short one, and basically each one of these cones, if you filter each curve with the spectral power for the wavelength, you will come up with a number. So basically you can characterize each spectrum with three numbers: the response for the short cones, the response for the medium cones, and the response for the long cones. And basically these are values that correspond to the R, G, and B values. Now, of course, that you have a problem that you will represent an entire spectrum with just 3 numbers, and this will mean that you could have different spectra, and you could have the same triplets. And if you have this, so in this case, you will have 2 different spectra that will appear indistinguishable, and this is the case here. You have spectra of real-world surfaces here. If you employ the curves that I was showing on the last slide, they will produce 3 numbers for each of the curve, and in particular for the white petal here, that is the green curve here, and for the magenta curve here, these 3 numbers will be the same, meaning that you cannot distinguish the spectra of white petal and the spectra of white flower. Now, in order to quantify color, usually what we have to do is to conduct a human study. So the spectral distribution, they are interpreted by the human visual system, and a human can say that it perceives some color. But in order to make a standard, there was some experiments conducted in the 1920s. So the experiment consisted in the following setup. We wanted to, so the experiment was conducted in order to understand which spectra will produce the same color sensation in different people under similar viewing conditions. There are like around 17 subjects that they got controls to 3 primary lights, and indeed these 3 primary lights were red, green, and blue. There was a light projected on half of a wall with a test light, and they had to combine the intensity of each of the primary lights in order to obtain the given light. So here is the setup. You have the subject here, so it's given a test light, and he has the primary lights at his disposal, red, green, and blue, and he has to adjust the intensity of these 3 primary colors such that it will match the testing light. Okay. So yeah, so I'll come back to what Andrei is saying later, but the idea is that you can use, so of course neural networks. So with of course that it will learn in every color space, but the idea is that you want to detect first the region where is your gate, and you can do it very easily using an HCV color space. So I'll come at the end of the lecture to address this point. Okay, and so this experiment it's related with trichromatic color theory, which says that basically, given three primary colors, you can mix and with weight W1, W3, W3. The primary colors P1, P2, and P3 in order to obtain a test color T. And here you have the entire experiment. It's explained in detail. Okay. Of course, that the primary color have to be independent. There is an exception that colorblind people cannot do this stuff. And the idea of trichromatic color theory was understood and was used since 18th century, where basically every color was encoded using only 3 numbers, the weights corresponding to the 3 primary colors. So let's do the experiment here. So you have the test color is this greenish color, and here in the right part you have a black one. So these 3 lights are basically red, green, and blue, and you have to adjust the intensity of each of the primary colors such that you will match the greenish color in the left. So if you start with, so P1 will correspond to red, P2 with green, and P3 to the blue stuff, to the blue color. And if you adjust the color, if you increase greenish at one point, you'll obtain the same color, meaning that the primary color amounts needed for a match are P1, P2, and P3 if you have used red, green, and blue. Now, if we go to the next experiment, here we have some reddish color in the left, and here we start with some magenta color. So it's a mix of basically of red P1 and P3. It's blue. Now we decrease the green and increase the blue, and we see that we only obtain some reddish color, which approaches to some degree the color that we want to match in the left part. And we see that actually we cannot match with the current colors, the red, blue, and green, the color in the left. But actually, if you modify the test color and add a little bit of P2, then you would match this color. So basically here it means that you have to subtract P2 from the initial colors. So here we would say that a negative amount of P2 was needed to make the match, because we added to the test colors. So here you would have that you need a negative amount of color P2 of green, which actually poses some problems, as when you want to display some color on the monitor, basically you have blue, you have blue, green, and red, but of course that you cannot produce a negative amount of green. Yeah. Now here you see the results of the experiment from 1920s, with I think 17 subjects, and you could see that for each of the subjects, the matching function for the RGB color space, they look very consistent. So you have so for example here, so if you take basically the average response for blue, for the blue color, for the red, and for the green, you will obtain this kind of curves, and this would tell you how much amount of color blue, red, and green you need to obtain any color from the one that were used in the experiment. So here you see you have the green color, which is about I think 545 nanometers. Here, so of course you have here it's 0 blue, 0 red, and I think it's about peak in green. Here you have blue. It's around I think 440 nanometers, and you have 0 spectral values in green and red, and it's about peak in the blue. Now, about linear color spaces. So you obtain, so linear color spaces are defined by choosing three primaries. And of course that the coordinates of a color are given by the weights of the primaries used to match it. So you need what are called the matching functions. And here, so these matching functions are the amount of each primary needed to match a monochromatic light sources of each wavelength. And you can see that the results obtained back in 1920s, you have these RGB matching functions here. So if you want to match colors from this region, you need to subtract red, which I said that this is problematic, and this is the one reason for which you have any also other color spaces. Now here, so you have the RGB cube. So 100 will correspond to red, 010 will correspond to green, 001 correspond to blue, 000 will correspond to black, 11 it will correspond to white, 011 is an intersection from blue and green, so it's cyan. 110 it's green and red it's yellow, and 101 is blue and red it's magenta. Now if you clamp the value for blue equals to 0, you would obtain this representation in the plane. So you have all colors where blue equals 0. So you have green, yellow, green, red, and here you have yellow. Here you clamp, if you clamp the value for green equals 0, you have some blue or red magenta color, and here you clamp the value for red, and you would obtain colors in green and red. Now, what happens if you slice the entire RGB cube? So, for example, you take the plane R plus G plus B equals 1. So you can see this stuff as doing the so you can see this slicing as basically you can approximate the value of the brightness with 1. Of course, that if you take a parallel plane with this one that goes through the value that goes to the value 3. So if you have R plus G plus B, actually you have only one color white, where you have the maximum brightness. And of course, that if you move this plane at the value R plus G plus B equals 0, you would obtain the minimum value of the brightness that will correspond to black. So you can think of these slice as by clapping the brightness of your colors to value, let's say 1, because this is the equation of your plane. And so if you do this, then you would obtain 2. So you go from 3D to 2D, and you obtain this two-dimensional representation of a color. And in particular, if you go to the plane R plus G plus B equals 1, this is called RG chromaticity, because you have red and green, and the blue color here it's 1 minus G minus R. And so in chromaticity, so basically you split the color into the brightness here. It's constant, equals to the value of the plane, and you have also the chromaticity that it will give you information about the ratio of the primary colors independent of the lightness, independence of the brightness. So you could take another plane parallel with this one, but instead of taking R plus G plus B equals 1, you can have R plus G plus B equals 0.1125, and here you can take this equals 3. Now, so we had the problem that for the RGB space, there are basically some colors that in order to match, you have to set negative weights for the red channel. So based on this, there was we come up with another linear color space, which is the XYZ color space, where actually in comparison with the RGB space, now you don't have primary color that they are real actually. So you come up with primary colors that are imaginary, but the ideal property is that you don't have now matching function that are negative. So all matching function corresponding to the three primary colors are now everywhere positive. So and here X, Y, Z, Y stands for the stands for the brightness, and X and Z basically accounts for the chromaticity part of the color. Z basically it's very close to the blue, and X it's a mix of response curves such that it will be non-negative. And if you look at the matching function, you see that now that for the XYZ matching function, these are different than the RGB matching function, and these are all positive. Whereas you have this the matching function for the red color here, it's negative. Now you can do the same stuff that we did here for the RG chromaticity. So you can take you can move from the 3D visualization to the 2D. So you consider the brightness to be constant, and you can obtain what is called the XY chromaticity diagram, where X is obtained based on the XYZ color space, and so X is X divided by X plus Y plus Z, and Y is Y over X plus Y plus Z. And now you would obtain this chromaticity diagram that basically will show you what kind of colors you can represent in every color space. So if we use this diagram, then we can see that in the RGB color space, so we have red, it's here at 100 wavelength. So and green it's around 400, it's 545, and green it's around 440. So now, because you have a color model, so because you have a linear color model, now all colors in the RGB space, if you are in the 3D, all colors are basically part of the cube. Now, if you represent the colors red, green, and blue in the 2D space, now all possible colors that you can obtain, and these are called gamut, are represented by all possible combination with positive weights. And of course, that if you do this in plane, you would obtain what is called a gamut, and here it is represented by a triangle. So if you take the center of the segment that links the green with red, of course, that you'll obtain yellow. If you take the center of the segment between green and blue, you'll obtain cyan. If you take the center of the segment that relates green and that connects red and blue, you'll obtain magenta. if you take the center of this triangle, you would obtain here white. And of course, that if you connect the blue with the white, then you will go to this will intersect this side in yellow, because yellow is a complementary color of blue. If you linked this vertex red with white, and this will intersect inside, because
2-3 zile, pentru că mai ai cât 2 pungi.
What?
E bună idee. Ideea mea. Ți-am
Okay.
ideea asta.
Did not understand this stuff. Okay. And if you connect the green vertices here with the white point here, you will obtain magenta. Magenta is the complementary color of green. Now, if you change the primary colors, so here in the RGB we use as primary colors red, green, and blue, and we obtain a triangle. So if you change the primary colors, you would obtain other gamuts. So, and here you have many different color spaces that I'm not gonna dive into it. So you have Prophoto, RGB, cyan, magenta, yellow, and black, and black that is used in for printing, standard RGB, Adobe RGB, and so on. Okay, let's look a bit at distances in color. So we have this XY chromaticity diagram from the XYZ linear color model. So, and here we have like 3 images, and we have some pixel colors from 3 pixels in the 3 images. And you see that if we look at the Euclidean distances between these 3 points, you see that these are not perceptually meaningful, meaning that a higher distance here does not correspond to the fact that these colors are more different than these 2 colors which have a smaller distance. So actually, this is because XYZ is not a uniform color space, and so the magnitude of differences is a poor indicator of the color distance. You can do some modifications and arrive in a color space where you have uniform colors, meaning that the distance is perceptually meaningful. Meaning, so here in the XYZ space, you see these ellipses. Basically, all the points on the contour of the ellipses are points that have the same distance with respect to the center. As you can see here, that you have elongated ellipses here, meaning that the distance in color from this point to the point here is the same as the distance from this point to this point. Whereas if you go to the UV color space, then you'd have a uniform color space where now ellipses they are more uniform. Now we also have what is called a nonlinear color space, HSV. Either you see it like a pyramid, or you could see it like a cylinder. So here the color is given by the hue, and this is given by the angle, by this angle. The saturation is given by the distance between the color and the center of your pyramid or your cylinder, and the value basically gives you how much brightness you have. So either you can use an HSV representation like a cone, or you can use a representation like a cylinder. there are some geometric transformation that transform the RGB space into the hue saturation value color space. So hue would mean basically what color you have, and so if you want to detect the red color basically will correspond to value to hue 0. Green will correspond to 120, and blue will correspond to 240. So if you want to go to the test sheet and recognize quite to detect the region where you have your grade, it makes sense to go from RGB to HSV and basically try to see what are all the pixels which has hue equals 0. That basically will characterize the pixel with red color. Okay, so here you have the geometric transformation that you can make in order to transform the unit cube RGB to a smooth cylinder HSV. You also I didn't put actually the transformation, but I think if you browse them you can find it easily. I only want to show you some examples here. I think this image I show you in lecture 2 or 3 in the beginning, where we talk about color images in the RGB format. So here you have 3 channels. You have the red channels, the green channels, and the blue channels. Now in the HSV color format, the red, green, and blue channels are replaced by other 3 channels, the hue, saturation, and value. So you still have 3 channels, but you have now different information. So the hue channel is responsible for the color. The saturation channel is responsible how much is your color saturated at each pixel, and the value will tell you how much brightness you have at each pixel, and you can play with these values and obtain different images. So for example, if you double the saturation of your pixel, you will obtain more intense colors. So you just modify the saturation channel for the input image, and you would obtain this much more vivid image. So you have a more yellow looks more vivid. If you double the values in the value, so you have hue saturation value. Another space that I didn't put here is hue saturation lightness. So here you double the lightness, the brightness in your image. So your initial image will look like this one. Other thing that you can do, you can subtract 0.2 from your hue channel, and basically this will change all your colors in your image. You go into your cylinder and see basically you will permute all your colors. And here you have and I think here what it is shown is that you increase the saturation, but you put a threshold, and you obtain this image in the right part. Okay, and if you look closely, you see that you have some red regions that are quite very saturated. So you see the red part in your motorcycle, and also the red part here, the red light of your car. So you could also do this kind of stuff in your in your project for the bonus point. try to saturate your colors, and then try to go for the hue channel and detect all the pixels that have hue equals 0 that will correspond to the red value. Okay. Okay. And now, so as I come to the last bit, to the last slide of the lecture, let's try to answer to Andrei's questions. So so actually this was one of the questions that was put back in the 2005 to 2010. Everyone was asking if you could do better if you have changed the color space. Actually, it has happened also to me. At one point during my PhD, I wrote a paper, and we did some experiments with the RGB color space. And at one point, we want to distinguish between windows that do cover objects from windows that do not cover objects. And we found out that instead of using RGB or HSV, if we have used LAB, this is another color space that I didn't use here. So if we are using LAB, then our method increased by 1%. So actually, we moved to this color space. What you say in theory is correct. So you expect that a neural network should be able to generalize no matter what color space you use. But my feeling from my experience is that for some particular task, you could have, like as I had, like 1% improvement if you move to another color space. So I don't have actually a very principled explanation why this happens, but I do know that back in 2010, when I'm doing my PhD, lots of researchers were asking each time what happens to your method if you change the color space, and the performance of the method could increase also up to 1%. So now so for your project, I would say HSV will be the one to go. So try hue saturation value, and you should detect quite easily red color. Also, you have the greenish stuff, so it will be quite easy for you to detect the red handwritten and also the green digits. So I will go for HSV. Of course, you can also use RGB, but if you look at the last slides, you would see that if you use the proper way HSV, you will detect very easily the handwritten digits. Okay, if you have questions. Okay, so there are two questions from Andrei and from Alexandra. So you don't need actually to extract the green digits. I am telling that this could be a useful information, an additional information, just to be really sure that you did the right thing. Of course, that you only need to extract the red color. Yeah. So, but actually, if you think for what we have to program next week, we will do some matching with shift features, and basically you want to match a rectangle in a perspective or in a rotated view with a rectangle in a scan view, and you can use information from the red handwritten region, and for the green green digits detected, to be really sure that your frames are in the right place. So I was telling that because of course that you only need to identify for the bonus points the red color, but for the entire project you could use the red information and green information, such that these will be useful cues for localizing your frames, the left frame and the right frame, especially in the scenario where you have a perspective or a rotated view. Okay, now going back to Andrei's questions. So he said, okay, so he says about RGB and YNC BCR. This is another color space. Maybe you're learning. Yeah, could be. Yeah, so it could be that your kernels would learn something for the structural information. So I don't have so much experience with this stuff. I worked with RGB, of course, HSG and LAB. I didn't work with this space, and I didn't try to train neural networks for different color spaces and see what are the differences for different tasks. Yes, so actually, yeah, so I didn't write I didn't read any paper that compare the performance of neural network trained on HSV versus trained on other color spaces such as LAB and RGB. So I will not I'll not make a statement here, because I don't know very well if there is such a difference when changing the color space in training neural networks. So my feeling is that it should not be, based on the fact that you have enough training data, and if there are, maybe just minimal, but I cannot say more regarding this stuff. Okay, yeah, cool. Yeah, maybe you find some papers where they study the difference between HSV and RGB or other color spaces from the point of view of training neural networks, and this would be quite cool to share with all of us. So if you have time, it will be quite cool to dig into this problem. Okay, it's kind of late, so some of you could go to Juliana's hour. So we stop here. Tomorrow morning I will do the same lab session that I did yesterday, last week. And the schedule for the next 2 weeks is that we're gonna cover. We try to arrive next week. So next week I'm not pretty sure that we're gonna make it to talk about the SIFT features, because you need SIFT features in order to match the perspective view and the rotated view for the last part of your project. I will think how to schedule the lecture such that at least in the lecture 8, so now this was lecture 6, in lecture 7 we'll talk about Harris corner detector, how to detect corners, and maybe in the 8th lecture we're going to talk about SIFT, but we will employ the SIFT features to match the perspective view and the scan view in a project. So I'm gonna look how to schedule my material such that by the end of week 8, and when we go into the holiday, when we'll have enough material such that you can solve with what we do in the lecture and what we do in the exercise class to solve the entire project. Okay, good. So we stop here, and we see with some of you Wednesday, and or otherwise we meet at on Friday for the advanced machine learning class. Okay, bye.